My name is Mike Casper and I work with the University of Colorado and Amazon Robotics. In this video, I'll be presenting our work on unsupervised metric relocalization using transform consistency loss. Visual relocalization frameworks ultimately seek an accurate relative pose between a query frame and a reference frame. Most solutions start by matching salient points in one image to their corresponding point in the other. Finding these image correspondences in dynamic environments, like we see here, can be exceptionally challenging. To address this problem, deep learning can be used to infer more robust image representations. However, training such networks require large datasets of ground truth image correspondences. Most likely these cannot be obtained directly, but instead computed using knowledge of the scene depth and relative poses between the cameras, which in turn requires additional sensing or restrictive camera placement. To circumvent this problem, we propose employing a second reference frame whose pose relative to the first reference frame is known. As we assume these two frames to be captured in a small spatial temporal window, we can obtain this relative transform using an off-the-shelf visual odometry pipeline. Using this configuration, we independently align each reference frame with the query frame. Our goal then is to learn a more robust image representation that maximizes the agreement between these two estimates. Here, image alignment is performed by finding the transform TQR that minimizes the photometric error between these two images. As common in direct image alignment, this is an iterative process performed in a coarse-to-fine fashion. However, we substitute the input images with feature maps and weight the residuals with saliency maps, both of which are inferred by our network. This optimization is fully differentiable, so we can directly integrate it into our loss function. The transform consistency loss is then computed from the two estimated relative transforms between each reference frame and the query image, as well as the provided transform between the two reference frames. Intuitively, we are using this provided transform to move both estimates to a shared world frame before comparing them together. Here we see two images of the same scene captured at different times along with the respective feature and saliency maps. In this qualitative assessment, we find the feature maps are quite similar despite large discrepancies in the input images, and that the saliency maps effectively mask out dynamic objects. Here we see a more extreme example with similar results. Using a synthetic dataset generated using the CoRL simulator, we analyze our saliency maps for several semantic classes. Here we compare the inferred saliency weights with those obtained using a uniform weighting strategy, which is indicated by the gray line in the bottom plot. Values above this line indicate a class is receiving additional focus, while values below the line indicate a class is effectively being ignored. As we can see here, our saliency maps successfully mask out dynamic objects, which may otherwise negatively impact image alignment. We evaluate the accuracy of our method using the GNNet relocalization tracking benchmark. Here we see the cumulative relocalization accuracy on the sunny overcast test dataset. This plot can be interpreted as the percentage of relocalization attempts, on the vertical axis, that were performed within a given threshold, shown on the horizontal axis. A theoretically perfect system would result in a horizontal line at the top of each plot, indicating that 100% of relocalization attempts were performed with zero error. Here we can see all the different weather pair datasets published with the GNNet benchmark. In all 6 scenarios, our method significantly outperforms other leading methods. If you'd like more information about this work, I encourage you to read our paper, referenced here, or to contact me directly at the following email address. Thank you.